Welcome back, everyone. In our previous lecture, we explored the heart of modern FTIR spectroscopy, that is, the Michelson interferometer. We saw how infrared radiation is split into two beams, how these beams travel different optical paths, and how they recombine to produce an interference pattern called an interferogram. We also learned that a Fourier transform converts this interferogram into familiar infrared spectrum. But today, we are going to move one step closer to real laboratory instrumentation. We will examine how this interferometer is actually integrated into modern FTIR spectrometers. And we will compare two major instrument designs, single beam FTIR systems and double beam FTIR systems. Take a close look at figure on the screen. This is schematic diagram of typical single beam FTIR spectrometer. At first glance, the optical pathway may appear complicated, but once we follow the beam carefully, the entire design becomes logical. Let us trace the path of IR radiation step by step. We begin with the broadband infrared source. The radiation travels toward the beam splitter. As we discussed previously, the beam splitter divides the radiation into two separate optical paths. In the first arm, the infrared beam passes through the beam splitter and travels toward the fixed mirror. The beam reflects from the mirror and returns toward the beam splitter. In the second arm, the beam reflects toward the moving mirror. This mirror continuously moves back and forth. Because the mirror moves, the optical path length of this beam changes continuously. Both beams eventually return to the beam splitter and recombine. Because their optical path lengths differ, the beams interfere constructively and destructively. As the moving mirror shifts position, the interference pattern changes continuously. This changing interference signal forms the interferogram. The recombined beam now passes through the sample compartment. Certain frequencies are absorbed by molecular vibrations in the sample. The remaining radiation reaches the detector, which converts the optical signal into an electrical signal. Now, here is something extremely important. The quality of the interferogram depends entirely on the precise motion of the moving mirror. Even tiny errors in the mirror displacement can distort interferogram and ruin the spectrum. This brings us to an essential component of the instrument. If you look carefully at the diagram, you will notice another small light source, a laser, specifically a helium neon laser. Why is this laser included? Precision, absolute precision. The Fourier transform requires extremely accurate knowledge of the mirror position at every instant. The computer must know exactly how far the mirror has moved during data collection. And we are talking about microscopic displacement, often measured in fractions of wavelengths of light. The helium neon laser acts like an optical ruler. The laser wavelength is extremely stable and precisely known. As the mirror changes position, the laser interference fringes provide reference markers. These fringes allow the computer to sample the interferogram at exact intervals. Without this reference system, high resolution FTI spectroscopy would not be possible. Now, let us compare this design with another important configuration, that is the double beam FTIR spectrometer. At a first glance, the system appears similar, but now observe the additional mirrors labeled M1 and M2. These mirrors create an alternating optical pathways. How the double beam system works? In a double beam design, the beam emerging from the interferometer alternates between the reference cell and the sample cell. Mirror M1 oscillates mechanically. For one moment, it directs the beam through the reference beam. Then, during the next movement, it directs the beam through the sample path. The mirror M2 operates synchronously with mirror M1. Its purpose is to redirect the alternating beam toward the detector. As a result, the detector rapidly receives the alternating measurements of reference intensity and sample intensity. Then, what is the purpose of double beam design? Why was this useful? Because older instruments suffered from source intensity fluctuations, detector instability, and environmental drift. By continuously comparing the sample signal with the reference signal, the instrument automatically compensated for these variations. Now, let us discuss the mechanical engineering behind these systems. The moving mirror must operate with extraordinary precision. Its velocity must remain perfectly constant. Even tiny vibrations or jerky motions can distort the interferogram. To achieve smooth motion, modern FTIR systems mount the mirror on frictionless air bearings. These air cushions minimize the mechanical friction and vibration. The mirror is typically driven using an electromagnetic coil system. This allows highly controlled mirror motion with remarkable stability. The Fourier transforms assumes precise sampling intervals if the mirror velocity changes unpredictably. The phase relationship becomes distorted and the resulting spectrum loses accuracy and resolution. Now, let us discuss the modern laboratories overwhelmingly favor single beam FTIR systems. Historically, double beam systems were preferred because early IR sources and detectors were relatively unstable. Continuous reference corrections was necessary, but modern technology changed everything. Today's IR sources are highly stable. Modern detectors are extremely sensitive and reliable. Because of this, continuous beam alteration is no longer essential for most applications. Modern single beam FTR systems use a much simpler strategy. First, the instrument records a background scan. This scan is taken without the sample. The computer stores this reference spectrum in memory. Next, the sample is inserted and scanned. The software instantly compares the sample spectrum with the stored background spectrum. Using this ratio, the computer calculates absorbance or transmittance. This approach simplifies the optical design, reduces the moving parts, improves reliability, and lowers instrument cost. That is why single beam FTIR spectrometer dominates modern laboratories today. Now let us summarize why FTIR technology revolutionized infrared spectroscopy. The advantages are over classical dispersive instruments are enormous. The first advantage is speed. FTIR system collects all wavelengths simultaneously. As a result, complete spectra can be acquired within seconds, sometimes even in milliseconds. This enables rapid analysis and high throughput measurements. The second advantage is high resolution. Modern FTIR systems achieve exceptional spectral resolutions, that is below zero point 0.1 centimeter inverse, are routinely achievable. This allows extremely precise separation of closely spaced spectral lines. The third advantage is excellent signal to noise ratio. Because the entire radiation beam is used simultaneously, FTIR instruments achieve much better signal to noise ratios than dispersive systems. This improves sensitivity and spectral clarity. Fourth advantage is accurate frequency determination. Now, this advantage is particularly important for modern digital analysis and especially useful for those who process spectral datasets using Python or software like Origin. Because all wavelengths are measured simultaneously and referenced using the laser system, FTIR spectra exhibit highly accurate and highly reproducible frequency measurements. In dispersing instruments, stray light can create serious distractions. FTIR systems dramatically reduce stray light interference. This improves baseline stability and quantitative accuracy. FTIR also enables powerful digital processing techniques. For example, background subtraction, spectral subtraction, signal averaging, and automated peak analysis. If you export the raw interferogram data into software like Origin Pro or Python, you can directly observe the extraordinary precision of the interference signal itself, even before the Fourier transform is applied. Let us summarize today's lecture, in which we have learned how modern FTI spectrometers are built around the Michelson interferometer. Signal beam systems record a background spectrum first and then compare the sample spectrum computationally. Double beam systems alternately measure reference and sample beam using synchronized mirror. Modern single beam systems dominate today because modern sources and detectors are extremely stable. FTI spectroscopy offer enormous advantages over classical dispersive spectroscopy, including high speed, excellent resolution, improved signal to noise ratio, and highly accurate frequency measurement. In our next lecture, we will step backward historically and examine the older dispersive IR spectrometers. We will see exactly how those classical mechanical scanning systems operated and why FTR technology ultimately replaced them. Thank you for watching, and I will see you in the next lecture.